record this meeting on this time. And yeah, just don't hesitate to ask questions or raise your hand to answer questions. It's highly encouraged, and you can also help other people learn different ways. All right. So first off, we'll go over a homework and homework review. So first problem, we actually changed it a bit because it was ambiguous before. From a standard 52 card deck, what's the probability of selecting 3 red cards in a row without replacement? I'll just do these myself since we already went over this material last week. And if you have any questions, you can ask. All right, so if we recall, there are, I already forgot whether there's suits or there are suits. There's spades, hearts, diamonds, and clubs. 2 of those are black and 2 of those are red. And there's all 13 of each, so half the cards, 26, are red initially in this deck. Half of them. Probability, the first one you select is red is 1/2, obviously. For the second card, let's see, there are 25 red out of 51 total. And then for the third selection, there's 50 cards left, whereas there are 24 red left. Now we can cancel a lot of numbers here as follows. And after we simplify this, this is just 2/17, which is the right answer. This is pretty simple, just like taking the probability for one card after another, multiplying it. And since it's without replacement, yeah, not too hard. All right. So second one. For randomly selected 10-digit number, what's the probability that the last 3 digits are all the same? Okay, so now note that we don't really care about like any of the other digits. So let's see, the last 3 digits, there's no restriction. They can be anything from 0 to 9. So the first one can be anything, 10 choices. And the second 2 must be equal to that. And the probability of that happening for each of them is 1/10 times 1/10. So it's 1/100. Note that like strategies like sometimes you want to fix a given thing like one of the digits and then calculate the probability for the other 2 digits based on that. All right. Sometimes it's very common to first fix something and then calculate probabilities based off of that, as in this problem, which would be easier than just going through all like cases. The first is 0 and the second 2 must be equal to. Let's here. Okay, let's continue. So if there are 4 green blocks and 3 red blocks in a bag, what's the probability of selecting 3 of the same color without replacement? This is kind of similar to what we did before, because we have to account for the cases green and red separately. So let's see, if there's 3 green blocks we pull, that's 4/7 times 3/6 times 2/5. Similarly, for 3 red blocks, that's 3 times 2 times 1, 7 times 6 times 5, because I'm kind of lazy. If we add this up, this is 24, that's 6, so it's 30/7 times 30 if you do some factoring. So it's just like 1/7 in total. Yeah, those are all the homework problems. I think they were fairly straightforward. They weren't too difficult if you understood what was going on last week. But if you have any questions, you can always ask me. Let's go on to today's material in that case. Sometimes you need to look at events one by one and use counting techniques like symmetry or casework. For example, 3 fair dice are rolled, and what's the probability that exactly 2 of the rolls are 1? All right, now I'll just like let everybody work on this for a short amount of time, and once somebody gets it right, I'll go over it. And meanwhile, you can also get started on the second problem, where Lisa shakes her piggy bank, which has 5 quarters and 5 nickels until 5 coins fall out. If they all have an equal probability of falling out at any time, what's the probability that the sum of the change is 85 cents? All right, so I see somebody got it right. Does anybody want to go present this? All right, Lewis, go ahead.
So like the first problem, you can use something called like binomial theorem. So this means that you have to choose 2 out of 3 roles to be 1. So three choose 2 ways. And then there is a 1/6 probability that you will choose a 1. So this squared times a 5/6 probability that you will choose something else. So this gives us 3 times 36 over 1/36 times 5/6, which is equal to 5/72.
Right. So I think at this stage, bringing in binomial coefficients is a bit complex. So I'll just do it like using a regular counting. So if 3 fair dice are rolled, exactly 2 of the rolls are 1. Well, you can think about it as 3 choices for the one that's a not, that doesn't roll a 1, or just 3 choose 2 ways to choose the one that are both roll 1. Either way, it's going to be 3 due to combo identities. And then the probability of the two getting 1 is 1/6 times 1/6, 1/6 squared, times 5/6 for the other one not being 1, since exactly 2 of them are 1. If you multiply this out, this is just 5/72. Otherwise, there are some other like slightly different ways to do it, but I won't really go over that since like this is simple enough. And now I'll give everybody a little bit of time to work on the second one. I think our TA Steven is here, so you can also private message him answers if you want to. And you can just send me the answer once you're done. haven't seen any correct answers yet, so because this problem does have a few parts to it, but I'll just go over it now. So first off, we want to determine what has to fall out in order to make the change 85 cents. We quickly estimate and we see that 3/4 has to do it. 5/4 would be 100 cents, or 4/4 would be 100 cents. And then 2/4 would be 50 cents, and 3 more nickels wouldn't be enough. And then we see 3 nickels, 2 pennies perfectly makes 85 cents and 5 coins. So next up is to find out what's the probability that that happens. So note that like since they fall out one by one and we wait until 5 falls out, obviously this is without replacement. And so the probability would be, sorry, whoops, it's messy. Let's say just 5 times 4 times 3 times 5 times 4 over 10 times 9 times 8 times 6 times 7 times 6, sorry. The 5 times 4 times 3 is for the 3/4, and then the 2 nickels are 5 times 4. And then the but however, we also need to account for the fact that like the quarters and nickels can like basically fall out in any order. And so we must account for like the symmetry in the orderings. So this is like basically the amount of ways to arrange 3 Qs and 5 Ps together, which is just 5 choose 2 in this special case, which is equal to 10. So we cancel out this, and then we just do some more canceling. So it's 1292. 6 times 6 is 36, 9. So we notice in the denominator what's left is 7 times 9, which is 63, and then the top is 25, which should be the correct answer, 25 over 63. So yeah, that's how to do this problem. I think like the noticing how many coins has to fall out isn't too bad, but you must account for like the what's it called, like the symmetry in a bit like arranging the quarters and nickels. I think some people may have like inadvertently done it as without replacement, and in which case the right answer should be 5/16 or just 10 choose 2 times 1/2 to the 5th, which is indeed 5/16, which it is okay, because it didn't really specify it that closely here. So yeah, if you got that, then you probably understood it just wrong, but you know how to do the counting, which is good. All right, so moving on to the rest of the stuff for today, we have some more examples. Probability is very important as it incorporates both counting and algebra a lot, so we have many practice problems. And we have 2 examples. The first one, Frank hits the bullseye on an archery target 1 in 3 times. So there's a 1/3 chance he hits, and a 1/3 and a 2/3 chance thus that he misses. If he fires 9 times, what's the probability that exactly 3 of his hits land on the bullseye? And you can get your calculators out to do this problem, since like you'll have to divide by some large powers, then that's all right. For the second one, there are a dozen eggs in a basket and 4 have been hard boiled. You select 3 from the basket, and what's the probability that only 1 is hard boiled? I would recommend doing the first one before the second one. It's a bit easier. But yeah, and when you submit the answer, do specify which problem you are submitting for. Thanks. For the second one, we just think of it as just like putting your hand in the basket and just taking 3 out. So it'd be like, I guess, kind of equivalent to picking without replacement. All right, so I see someone got number 1, so we'll just quickly go over that as it's not really that hard anyway. If Nathan, you want to go over it, sure.
Okay, well, when I'm doing probability problems, I always keep timesing the probabilities together. So in this problem, I need 3 bullseyes and 6 misses. And 3 bullseyes, you will get 1/3 times 1/3 times 1/3, or 1/3 cubed. And then for the misses, it's 2/3 to the power of 6 since you missed 6 times. And then you can rearrange the misses and the bullseyes in any way. So it's going to be 9 choose 3 ways to arrange them. And then just pull out the calculator and solve the question.
So it should come out to about 0.273, which means that about 27.3% probability that exactly 3 shots land in the bullseye. All right, so yeah, that's pretty good. That's not too hard of a problem, at least to think mathematically. Of course, you need a calculator to do it probably, but yeah, it's not too bad. You just choose 3, or you just choose 3 to hit, and then you multiply the probabilities together. This kind of like this often shows up as like a small sub problem when like solving problems. So yeah, just like be aware of that and understand it. Now I'll leave you to work on the next problem. The one with the eggs in the basket. Again, treat it you can treat it as without replacement, depending on how you're thinking about it. All right, so I see somebody got the second one correct. Do you want to explain it, or should I?
Okay, I can explain it. So basically, first we find the probability of getting a hard-boiled egg. So that's 4/12 multiplied by the probability of not getting a hard-boiled egg. without replacement, that's going to be 8/11 since we took one egg already, and then times 7/10, which is finding another non-hard-boiled egg. And then you multiply all of this by 3 to count for like which egg can be hard-boiled out of the 3 eggs, and you multiply all those together to get 28/55.
Yeah, that was like very excellently, smoothly explained. As he said, you go on first hard-boiled egg, 4 out of 12. Then times 8 remaining non-hard-boiled eggs out of 11, then times 7 out of 10 for the second hard-boiled egg, and then times 3 to account for the ordering. Which one can be the hard-boiled egg in this case is enough to like suffice to reason that there are 3 ways to order, and then you just like cancel and then solve, and you will get 28/55, which is just a little over 1/2 by coincidence. And yeah, that's basically all there is for this problem. Yeah, Nathan, do you have a question?
Well, I thought that should have been without replacement, just so that the possibility of you somehow choosing the same egg twice doesn't happen. But
Well, I see like the way I think the problem meant like since you have just like a batch of eggs and then it's just like you scoop 3 at once and take them out, and you can equivalently consider this as taking one at a time without replacement. So yeah, that would be my reason like why I think this implies that it's without replacement. But you can do it as a separate problem with replacement too. So yeah. So next we have casework and probability stuff. So as a reminder, casework is an organization strategy used in many counting problems. Split the possibilities into cases that are easy to count and then add them. You have to use casework if computing compound probability doesn't work, even if it seems like it should, due to a different number of choices depending on sometimes the order in which you pick things can influence what happens, unlike what we've been seeing most of these problems so far, and other factors as well, depending on what the problem is, to be honest. For an example, Oleg rolls a standard die thrice. What's the probability that the third roll is greater than the sum of the first 2? This definitely does require some casework, although if you try it out, it's not that bad. So I'll just give everybody a little bit to do this. Right, so I see someone's gotten it right. Well, if you want to explain, you can go ahead, or if not, I will explain it. All right, yeah, Nathan, you could just unmute and go ahead.
Okay. Well, I kind of just counted the number of ways that you can have the sum of the first two be less than a third. And in my cases where the first two summed up to 2, and the only way for the first two to sum up to 2 are 1 and 1. And then for the third die, you can roll 3, 4, 5, or 6, which gives you 4 cases. I mean, four ways to do it. If the sum is 3, then the first two can either be a 2, 1, or a 1, 2. And the third one can be a 4 or 5 or 6. And two ways for the first two, and 3 ways for the third. 2 times 3 equals 6 ways for sum 3 case. For sum 4, the first two can be 1, 3, 2, 2, or 3, 1. And the third die can be 5 or 6. And then 3 times 2 equals 6. If the sum equals 5, then the first two can be 1, 4, 4, 1, 2, 3, and 3, 2, which is 4 ways. And then the third die can only be 6, which gives 4. And then adding them together and then dividing by 6 to the power of 3, then simplifying is 5 over 54.
All right, yeah, that's right. So basically how this works is that you can either do casework on the sum or what number you roll. Either one is fine. I'll just go with the sum since that's what Nathan did. The sum can be 2, 3, 4, or 5. In order to have any non-zero probability associated with it. If the sum is 2, you have 4 choices for the third die roll. So there's actually I should just go with what's here. 4 options for the die. One way to roll that sum. So it's 4 times 1 is 4. Second one, and to sum the 3, you can get 1 plus 2 or 2 plus 1. And then there are 3 choices for the die. So 2 times 3, 6. For the sum adding up to 4, we have 3 ways for that. 1 plus 3, 2 plus 2, and 3 plus 1. Be wary of the fact that you can swap the numbers on the die if they are different. And in that case, there's 3 ways to roll the sum and 2 ways to roll the die, also giving us 6. And it's pretty symmetric in the last case. The sum can be 5. There's 4 ways: 2 plus 3, 1 plus 4, 4 plus 1, and 3 plus 2. And the die can be rolled in one way, just a 6. So then we have 20 total ways if we add all of this up, over 216 total possible die rolls across all possibilities. 6 cubed. Simplify it, we get 5 over 54. All right, yeah, good work. So yeah, that's how to do this problem. Note that you can do casework on multiple things. In this case, both casework on the third dice roll and the sum is not too bad, but just be wary of your choice for casework. There are some choices that are a lot easier and tractable than others for certain problems. So don't hesitate to change your thinking a little bit if one way seems too computationally bashy or not worth the time. All right, and now with that said, let's do more practice. So we'll practice these problems involving counting techniques like multiplication or casework. So 3 numbers are selected at random without replacement from a bag containing everything from 1 through 9. What's the probability that 3 are consecutive integers? And the second one, a homeroom has 7 boys and 5 girls. The teacher randomly selects 2 representatives to serve on student council. And what's the probability that the teacher selects one boy and one girl? So I'll let you guys work on these. I would say they're not that far off in difficulty. You can do either one you want, but just please specify which one you're submitting, as always, when I assign more than one problem on the board. All right. So it seems like there are people who have hit the mark on both of these. For the sake of time, I'll explain these. Although if any new hands want to answer these, then sure. But so for the first one, well, we do casework on what the set of three consecutive integers are, starting with 1, 2, 3, 2, 3, 4, and we can go all the way up to 7, 8, 9. And being consistent and counting based on the first number, we see that there's from 1 to 7, there are 7 such sets of these. So we know to multiply whatever probability we get by 7. So we have 7 times the first number we choose has 1/9 chance of being chosen, then times 1/8 times 1/7, and pretty simple. But note that you can choose those 3 consecutive numbers in any order, being 3 factorial. The 7 just cancels out with this, and the 3 factorial 6 over 7, 9 times 8 would be equal to 1/12. So 1/12 is your answer for this problem. And note that often, like in some of these casework problems, you can like skip through a lot of work if the cases are identical, but you just be sure, be like really confident that they are identical and make sure you know why. Like that, like if I ask you could explain why like all these cases are basically identical to each other. Although often at this level, I find that like the cases are like pretty identical and you can simplify it a lot. For the second one, homeroom has 7 boys, 7 girls. The homeroom teacher randomly selects 2 to serve on student council. What's the probability 1 boy and 1 girl are selected? Okay. So for our denominator, let's just treat it as choosing 2 people. How many different pairs can we choose? That's just 12, choose 2. We don't care about like swapping within the pair. And well, okay, how many ways can we choose the 7 boys and 5 girls? Well, 5 choices for the girl, 7 for the boy. That makes a pair. So this is 35 over 12 times 11 over 2, which is 35 over 66. I guess a lot of people did get kind of like messed up, get 35 over 132, but note that means like, let's say you chose person A first and person B second. If you do 12 times 11, then it's possible that you choose person B, and then person A, but then you treat this as different from that, which means that you would have to account for that by doing 2 times 5 times 7 in the numerator too, which is like a bit unnecessary. So I think it's better to just in this case treat like choosing a group as like choosing without order. Just be careful that as long as you're consistent with what order you chose to like mark as distinct and not, you should always get the right answer, but like for different problems, it's more convenient to use different tactics in that respect, that regard. So yeah, this problem is 35 over 66. Make sure that we don't fall into like that kind of pitfall for 35 over 1 over 30 over 132. But yeah, that's all there is. This is not too difficult. All right, so these problems might be some of the more difficult ones in today's class. So actually, I'll have you guys first do the second one. 26 letters of the alphabet are placed on tiles and randomly separated into 2 equal piles. What's the probability that the word math can be found in one of the 2 piles? Okay, so I don't want to make this too complex. So we can just treat it as being equivalent to all the tiles M, A, T, and H in the same group. We can treat the problem as being equivalent to that. So we want to find the probability that all of these tiles are in the same group. I'll give everybody a little bit to work on this. You might want a calculator to simplify, to like cancel out some numbers, but the answer should be like a fraction whose denominator isn't too large in the end for this problem. All right, so first I'll go over the second one. Admit there's like a ton of annoying calculation in it. Or actually like a lot of stuff cancels, but still it's kind of tedious. So we have first that like 26 letters of the alphabet. What's the probability that math can be found in one of these 2 piles? So the probability that math can go, so math will take up 4 spots, right? Whereas there are 13 total. So our answer numerator should be 9 choose 4. Or not, sorry, not 9 choose 4. What am I saying? Should be 22 choose 9 more to go in the slot, the same group with math. And then we divide by 26 choose 13 in total for like choosing the 13 to go in our group. However, notice the fact that this 26 choose 13 right here, we have to divide this by 2. Why? Well, think about it like this. Let's say you have these letters, and that these are the two different groups, right? Okay. So in reality, the amount of ways to choose like the tiles in this group is 26, choose 13. You choose the first 13, and then the other 13 left, you have to choose 13 of those. So it's really this, which means you choose the first group first, the second group second, right? Okay, so if we can choose this first and then choose this second, or we can choose this first and choose this second. But if we do 26 choose 13, well, times 13 choose 13, we count both of these as like different things. So we have to divide by 2 factorial, which is just 2 for that. However, this isn't really quite an issue for the other case, since it's not symmetric, as in like you can't just swap the groups, and you can't just like swap the groups since like math is in one of the groups you've determined, and you're basically either choosing 9 to be in the same group, or you're choosing 22 choose 13 not to be in the same group. And I think in the end this should work out to 11 over 115 if you do the math. So yeah, that's it. About this group thing, you might want to be careful about like this dividing by 2 factorial thing for this problem up here, which I will give you a little bit of time to work on. All right. So yeah,
Right.
I'll let you just work on that.
I actually didn't need to use the calculator for this, the second one. Like I didn't calculate all that combination stuff.
Yeah, you can probably just like, I don't mind if you use a calculator on it, but certainly you can do it without one, of course.
Yeah. Well, actually, I used a totally different way where there's absolutely no need to be using calculators.
Yeah, that's fair. There are like many different ways to solve these problems. Sometimes like some ways, I guess multiplying things one by one is less tedious, but yeah, it doesn't make a big difference after all. You can just cancel more at the end. But I'll let you all work on this first problem now. All right, so now I'll go over this problem. Okay, well, first off, what's our denominator going to be? Following our discussion for the math tiles problem, we see that it's going to be 12 choose 4 times 8 choose 4, and there's an implicit times 4 choose 4 over 3 factorial, as there are 3 groups, and we don't want to like double count picking them in a different order. And what's the numerator going to be? Well, for that one all-girl group, 7 choose 4 ways. 7 girls, we choose 4 of them to be in that group. We don't really care what happens in the other group since there's no overlap or double counting or anything happening among them, except of course, just like before, 2 groups out of 8 kids, we have to do 8 choose 4 divided by 2 factorial. Now this cancels with that. This cancels out to make a 3 in the numerator. So it's 3 times 7 choose 4 over 12 choose 4. 3 times 35 over 495, I believe. Or you can leave it factored. This is equal to 7 over 33, as I believe is the correct answer. Now, again, if you have any questions about any of these steps, don't hesitate to ask, since I do go through this, I guess, somewhat fast now. So yeah. Always make sure that you account for make sure there's no double counting. Like, let's say if I change this 7 here to a 9, we couldn't quite do this because, like, well, what if there's there could be 2 groups of all girls too. So yeah, just beware of double counting and all that stuff. Now we move on to probability and complementary counting. So remember, complementary counting is just counting what you don't want. In the case of probability, you just subtract this probability from 1, just like counting, you subtract what you don't want from the total. This is especially helpful in problems which contain something like at least 1 or like at most or similar phrases. Really, it's very similar to counting. The same phrases will indicate complementary counting, both counting and probability, as they are like very closely tied together. The example is the chance of rain for each of the next 5 days is 25%. What's the probability that it will rain at least once in the next 5 days? Express your answer to the nearest tenth of a percent. I assume most of you don't really have powers of 5 memorized, so you can use a calculator for this if you want. You'll probably need it, and you can just send me the answer when you're done. This is pretty straightforward, just like plugging it, just like get the expression and plug it in. All right. So I'll go over the first problem. Well, I haven't seen any correct answers so far. It could be like easy to mess up in some places. So what's the probability it rains at least once in the next 5 days? Well, the complement of that is simply that it doesn't rain in any of the next 5 days. Well, what's the probability it doesn't rain on one day? It's the complement of 25% or 75%, 3/4. In which then the answer would just be 1 minus 3/4 to the fifth in terms of probability. And then convert that to percent. I think it was about like 76.3%. 1 minus that. Be careful not to like calculate 3/4 to the fifth and put that as your answer by accident, or like accidentally do like 1 minus 1/4 to the fifth. There are like a lot of places surprisingly you can go wrong, and many people, including I, have suffered from these kind of like silly mistakes. So whenever you're using complementary, first of all, make sure that that complementary counting will be simpler than just counting it directly. And secondly, more importantly, make sure you don't make any such mistakes. All right, now second problem. You're playing cards and need a 5 to win. There are 9 cards left and 2 are 5s. If you select 4 cards randomly, what's the probability you get at least 1 5? Now this is also complementary, as you can see, the word at least one there. All right, so I see someone got it. If they'd like to explain, that would be all right, but I can explain too since we're running a bit long time.
Okay, so basically, the complementary of getting at least 1 5 is getting no 5s at all. So it's 1 minus, and then the probability of getting the 4 cards that are not 5s are 7 over 9 multiplied by 6 over 8 multiplied by 5 over 7 multiplied by 4 over 6. And then simplifying all of that just gives you 5 over 18. So 1 minus 5 over 18. So then it will just equal to 13 over 18.
Yeah, that's correct. So he did it just like doing it as some of the earlier problems before. We just calculate this probability of getting the cards that are not all cards that are not 5s, but just how I thought about it too. That's pretty much like the way to go here. But I just directly did 7 choose 4 over 9 choose 4. Know that these are both correct answers since they are consistent with distinguishability and ordering. This treats like the order in which you pick the same set of 4 cards as different, and the denominator does too, whereas I just treat it as the same set of 4 cards would be the same thing. So thus, both answers would yield 13 over 18, no matter which way you did it. And yeah, that's correct. Now we have one extra practice. I know we're running a bit late. So there are 9 blocks in a bag, 3 red, 3 white, and 3 blue. 3 blocks are selected at random without replacement, and what's the probability that at least 2 of them are different colored? And the second one, 3 students are randomly selected from a group of 12, including Billy and Adam. And what's the probability that Adam's selected but Billy isn't? All right, now I'll leave everybody to do this. Now that think back to everything we've done so far, complementary counting, but do not forget like the combinations, combinatorical things we just discussed earlier in the class. You can submit me your answer. Please specify which one you're submitting for. And yeah, I'll let you work on these. right, okay. Now somebody got the first one right. I'll just quickly go over that. So what's the complement? The complement would be all three blocks being the same color. Well, there are three color choices for what color that common color of all three blocks is. And then we can just treat it as 1 over 9 choose 3 in each case. Since like, well, if we just treat like the amount of the colors of the blocks we chose as the distinguishing factor, not the order, it makes it, I guess, a little marginally simpler. And so it's 3 over 9 choose 3. I believe that should be 1 over 28. If you or 1 over 28, if I calculated that right. And then you subtract that from 1, it's just 27 over 28. And I'll leave people to work on the second problem after. So yeah, just try that. All right, for the sake of time, I'll go over this. Just a note, if I reply to you in chat and say that I think you're kind of close, slightly off or off, if I say you're kind of close, that usually means that your answer, the numbers in the fraction, at least like share a lot of common factors with like the answer. And if I say you're like only slightly off, it's usually because I can tell which step you missed to get like the wrong answer you did. So I guess like just keep that in mind whenever I respond to you. Anyways, onto the problem. So we want the probability that Adam's chosen Billy isn't, right? Now in total, again, we can just say 12 choose 3, choose like 3 students. And then on the numerator, well, one of these guys is Adam. And then so we fixed one spot. The other 2 spots have to go to people who are not Billy. And we've already chosen Adam, so -1 choice. We can't choose Billy either, minus another choice. So we have 10 choose 2 left. So this should be 45 upon 220, which is equal to 9 over 44 is the final answer for this problem. So in general, in counting, you just need to be like really careful about ordering, being consistent across your multiple cases. What is the total, whether or not you have to subtract it from 1 due to complementary counting, and like many other things too. So yeah, it would be good to keep all of this in mind. I admit like counting is tough. When I was learning counting, I would often make like small errors that would lead me to be off by a certain factor or something in my reasoning. So yeah, just be aware of that and make sure that you justify every step that you do so that you are much less likely prone at least to make logical errors. And with that, class is over. We will post the homework shortly, probably by tomorrow. And this was also recorded the whole way through, so I will get that up once it finishes uploading. And yeah, see you all and have a great Christmas tomorrow.
And also,